I've discussed the kernel trick in detail, but so I'll just say a few words about the specific sort of training in the case of logistic regression. And the details are there in the notes, so I'll just highlight a few items, right? So basically, your log likelihood ratios for the training points, which are W transpose phi, now that W is basically a linear combination of these feature vectors, it's taken to be that way. This is A transpose phi transpose phi. And of course, now with the kernel trick, we are not really specifying the feature vectors explicitly. So this is just in the notation we had introduced, K, X, Xi. So this is the correlation between all the feature vectors, training feature vectors, and the ith feature vector, right? So basically, this is an n cross 1 matrix where of basically k x1 xi down to k xn xi. So that's what these zi's are, and of course the probability of the ith label being 1, yi hat, is still sigma of zi. Of course, now it depends. I'm going to write it out explicitly. Sigma of A transpose phi transpose phi. The cost function is still the cross entropy function, but now I'm going to think about it as a function of A, which is minus summation I equals 1 to n, the cross entropy function yi log yi hat, 1 minus yi log 1 minus yi hat, right? That's the cross entropy function. So basically everything proceeds exactly the same way. I'm going to take the gradient of this. I'm going to take the Hessian of this. And I can think of doing it one term at a time. And the key component of this will become something like the gradient of yi hat. Just like you were taking the gradient of y hat with respect to W, now you're going to take it with respect to A. And you can see, just as before, that using the chain rule, so let me write it out, delay of sigma A transpose phi I. As we know, the derivative of the logistic is the logistic times 1 minus the logistic. So basically, if I differentiate sigma with respect to its argument, I'll basically get sigma times 1 minus sigma, which is yi hat times 1 minus yi hat as before. And then I'm just going to get the derivative of the gradient of this term, and that is just phi transpose phi. So that's the kind of change you have. And of course, this, what is this? This is k x xi, right? And so when you put all these together, just like before, you'll get things like this will become kxx times y hat minus y, taking the same steps as before. And I'm not going to go through those details because I think it's really good for you to do it yourself. And the Hessian using similar techniques will be just kxx times the reweighting matrix times kxx, and the reweighting matrix is the diagonal of these yi hats, 1 minus yi hat terms, right, as before. So and then you have the Newton method as before. So I would very much encourage you to go through the details yourself and make sure that you're comfortable with the application of the chain rule in this context. The one other thing to mention is the notion of regularization. In regularization, we are putting a constraint on W transpose W, but W is now phi times A, so we have A transpose phi A, and again we are not explicitly specifying phis. This is just A transpose, the inner products between all the training feature vectors. This is an n cross n matrix of all these k, xi, xj functions times A, and then we basically have the gradient and Hessian of this term that contribute to the overall iteration. So I'm going to not talk any more about these details. You can go look at the notes for phis. This is just A transpose, the inner products between all the train n cross n matrix of all these k, xi, xj functions times A, and then we basically have the gradient and Hessian of this term that contribute to the overall iteration. So I'm going to not talk any more about these details. You can go look at the notes for that. One last observation is about inference. When you're given a new data point x star, you want to make a prediction about its label y star, and remember what you have is z star is w transpose phi x star, and w now is the capital Phi, all the training feature vectors times some optimal w opt, basically w opt, whatever you have found after your training. So of course this is A opt transpose phi of x star, and again we are not explicitly dealing with phis anymore. We are just we have a kernel that tells us what to do, and this is just k x star, and this is of course it's a n times 1 vector. So this is one disadvantage of the kernel trick. If the number of data points is large, you actually, for a new inference point, you actually have to compute these kernels with respect to each and every one of those training points, right? So you have to keep those things around to compute that. So that's one disadvantage of the kernel trick that we surmount by going to techniques like support vector machines, for example. What else? One more thing. Of course, if you want to make an this is z star is of course your log of the probability of y star equals 1 given x star divided by the probability of y star equals 0 given x star. So hard decision just means, well, if z star is positive, that means the top is bigger than half and the bottom is less than half, and I'll decide 1. If z star is negative, I'll decide 0. So basically z star bigger than or less than 0, I'll make decision 1 or 0. That's the hard decision. And the soft decision is z star itself, or you can spit out the probability of y star equals 1 given x star as sigma of z star. So this is your hard decision and this is your soft decision. So there's nothing new about that, but I just want to mention that.